Much has been written of the history and use of the golden section. The history, use, and claims of the golden section are highly debatable as it predates documented history. The purpose of this project is to elaborate upon the information that Ching presents, to point out the golden section's unique qualities, and propose methods of how to apply its qualities to the design process. The golden section has been referred to by several names over the last 3 millennia: golden ratio, golden mean, extreme and mean section, divine proportion, divine section, golden cut, and sacred cut, to name a few. In modern mathematics, it is referred to by the Greek letter phi, which represents an irrational number with a never-ending decimal. The golden section, as Ching says, can be defined as a ratio between two sections of a line, or the two dimensions of a plane figure, in which the lesser of the two is to the greater, as the greater is to the sum of both. And once again, it may be a bit vague as to how this definition and algebraic equation applies to design. How can we actually apply the golden section to a design? First, the figures to the left will need to be further explained. The first method is creating the golden ratio by extension. The geometric constructions of the golden section in these videos are referenced from a book by Rachel Fletcher entitled Infinite Measure. Rachel Fletcher is a faculty member of the New York School of Design and a regular contributor to the Nexus Network Journal, a dedicated venue for scholarly research in architecture and mathematics. We're drawing the golden section using a method by Rachel Fletcher. This geometric construction ensures a perfectly drawn square with equal sides and square corners. From the middle of the square, you'll swing an arc from one corner across. Draw a baseline and swing another arc. This creates the basic rectangle for the golden section. Here are the two sections that Ching is referring to, and those two add up to the sum of the two together. Interestingly enough, there's only one specific spot on this line where that can occur. The height and width of this diagram would show the two dimensions of a plane figure. However, to better describe the golden ratio, we would use this one here, as we would say the two dimensions of the width and height of the smaller rectangle equals the length of the larger rectangle. Next, Ching shows dividing a specific line into the golden ratio. And here we will use our previous diagram to demonstrate the relationship of the two. Again, we're using a method by Rachel Fletcher from her book Infinite Measure to draw this diagram. If we take this dimension from the diagram we just constructed, it matches in the exact same spot as the previous diagram. And then we take the next smaller dimension, or the minor dimension, and apply that it also hits exactly in the same spot. How would these concepts apply to design? If you were designing a custom-built door that must be 36 inches wide to meet specific building codes, then you would use the extension method with the 36 inches as a base or beginning dimension and extend it to construct the golden section diagram. This diagram provides you with an unlimited sequence of dimensions, all related by the same ratio. The division method is used to divide any random length at the exact spot to give you the major and minor lengths that relate to the total length by the same ratio. This diagram is used to geometrically demonstrate the golden section. For design purposes, it would only give you 3 dimensions to work with. Design an entry door using the golden section. Use 36 inches as the width of the door. This dimension can be referred to as the base dimension. To begin this drawing, I'm going to use the scale of 1 inch equals a foot. With the use of a parallel bar on a drafting table, I'm using a slightly different approach than that of Rachel Fletcher. However, I still need to begin with a square that is perfectly square on all 4 corners and all sides are the same length. This square represents my 36-inch base dimension at 1 inch equals a foot scale. I am using the extension method oriented vertically. Using this method, I have broken down the original 36 inches into smaller proportional units. These units are color-coded for reference. Next, I transfer that 36 inches as the width of my door. I draw 2 parallel vertical lines from those 2 points and work to establish the height of the door. I use the height of the diagram plus the same 36-inch square from earlier to give me the total height of my door. Then I use individual ratios from the golden section diagram to create the stiles and top rail of the door. Next, I choose a size of the bottom rail directly from the diagram. Continue to select dimensions from the diagram to create the rest of the details of the door. The color coding represents each element of the door and how it relates to the golden section diagram. Each part of this door, the length to the height, and every element relates back to the golden ratio. Using these ratio ties all the elements together as well as to the overall form of the door. To begin, I'm using the length of my index finger as the base dimension. Previously, when drawing the door, we didn't go into detail of how to construct the golden section diagram. That's what we're going to do here, using that base dimension of our index finger. First, you need to establish a perfectly perpendicular line to your baseline. Since we're not using a parallel bar for this, we're going to construct the entire thing geometrically, using nothing but the compass, the pencil, and the straight edge, and a pair of dividers to transfer dimensions. We will be using the geometric construction demonstrated by Rachel Fletcher. First, we create 4 intersections which set up our square with right angles and equal sides. From the center of the top and bottom of the square, we will swing arcs from the corner of the square and connect those 2 points with a vertical line. And once again, we have created that unique intersection where B is to A in the same ratio that A is to C. We continue this process on the next rectangle by transferring this dimension horizontally to the other side and pull a horizontal line from those points. The diagonal line indicates where this intersection is. Continue this process at each intersection of the diagonal line to create an infinite number of rectangles that relate to the previous by the same ratio that governs the entire whole. Continue this process to an appropriate smallest rectangle. Images of the golden section often depict it with this spiral imposed over the diagram. This is the reason that it is so often associated with the conch shell. However, they are not the same thing. A conch shell creates a logarithmic spiral that develops from the same center. The radius vector changes constantly around this center. The spiral created by the golden section diagram is not an logarithmic spiral because each radius begins at a different center point. This misconception creates a ridiculous amount of images and theories about this spiral, when in actuality, the only purpose of the spiral is using each arc to demonstrate the square, much in the same way that we created the original square with arcs to each corner. Referring back to the extension method, we can use this arc to extend our original diagram to a larger golden ratio diagram. In this view, we have reoriented our original diagram and used the arc to extend our diagram. The length of this new extension relates to each part of the original diagram using the same ratio as the entire whole new image. If you geometrically construct a pentagram from one of the lengths from the golden section diagram, each and every part of that pentagram will be the exact same length of each and every square of the golden section. Connecting the intersections of the inside of the pentagram will create a series of repeating pentagrams that are reduced by the same proportion as each square in the golden section diagram. We began this diagram of the golden section using the length of our index finger. From the diagram of the golden section, the next reduced length equals 2 digits of that index finger. The next reduced length, 1 digit of our index finger. Our finger descends in size by the same ratio as both the golden section diagram and the pentagram. Once we extended the size of our diagram, those proportions relate exactly to further extensions of our hand and body. The entire length of our extension is the length of our forearm. Observations of a leaf on this diagram reveal the length and width of leaves also closely resemble the golden ratio, connecting the human body's proportions with the golden section's proportions, the pentagram proportions, and the proportions of nature.